I hereby open the session. Mr. Doctoral Candidate, the Board of Conferral of Doctoral Degrees of Utrecht University now grants you the opportunity to defend your dissertation in public. I invite the first opponent, Professor Rowling from the Australian National University of Canberra, to speak.
Thank you. Geachte kandidaat, I would like to jump straight away into some of the plume physics that you have employed in the thesis. And in chapter 4 on the Black Sea, I may be confused, but I seem to miss something. I'm referring to the mixing parameter you use for the inflow plume of the water from the Mediterranean, and I think you resolved that with CFM, which in table 4.1 says is empirically determined, but it is not specified how that was done. Can you begin with explaining maybe how you empirically determined that?
So we know hooggeleerde opponent. Yeah. We know what the current state is, and we also know the state before the opening, right? Yeah. So then we can basically tune the model so that it works for those two situations, and that restricts the parameters quite a lot. Okay. And in the end, it turned out that parameter was not very critical. So if it was basically between 0.3 and 0.8, the results were basically the same. Okay. And the values outside of that range were just not realistic, I think. Right.
And maybe you can then also explain that in the first part of section 4.6, the discussion, you then seem to discuss these things in terms of a partitioning factor, which is a different one, C03. And you set that as a simple percentage point of the partitioning between the flow between the surface and the deeper boxes. Is that right?
But that's the C03. That's a different factor, right?
It is different.
So that's that's for when the water sinks. Yeah. That's the mixing with the deep water.
So you basically specify the mixing. I was sort of a bit puzzled why. With plume mixing, there are some good physical routines that you could implement. For example, the work from Price, and so it seemed to me that you make some very definite and rather subjective stationary choices where you could actually resolve these things with a fairly straightforward physical routine, and that could also then look at the water entrainment. So if we continue on that in chapter 5, then we are back to the Mediterranean, and in the methods you state that if a strait accommodates intermediate depth inflow into the open basin and the density of the water it carries exceeds that of the deep water, the flux will sink into the deep water box. Yet the sentence before that you suggest that you may in fact be considering some sort of a priori partitioning. But it's not specified, and as a result, it remains unclear what you're actually doing.
So the factors are in the model code in the repository that's linked. Yeah. I don't know them by heart, but if I'm not mistaken, then part of the inflowing water that sinks also mixes into the intermediate water. Okay. Entrainment. So but in practice, we're talking about the flux from the marginal basin to the open basin, right?
Yeah.
Or
yeah. And if you then compare that with the Black Sea, I mean, you there considered specifically specifying the partitioning between water going into the surface and the intermediate box, but here it seems to be done differently. Is that right?
That's right, yes. Okay. Because for the Black Sea model, we only have a surface, an intermediate layer, and a deep water box. Yeah. Right, and whereas in the next chapter, we also have an intermediate water box. Yeah. So for the Black Sea chapter, we have to make some more simplifications to make it work with that configuration. Okay, so
have you considered looking at plume and entrainment physics, etc., instead of the partitioning?
I have considered it, yes, yeah. And that could also be something to look into for when we're going to publish this chapter. Definitely.
Okay. So is there still some time?
Yes.
Yeah. Okay, so let's go at something else. In chapter 5, there's a very interesting analysis of the shorter term variability. I mean, in general, I think you're really touching on some really interesting stuff in an innovative way throughout the thesis. This was, for me, a very interesting analysis of the short-term variability, but what I'm missing is a first-order test. And you know, you are looking at these freshwater inputs, and how much goes into which box, etc. But how you could test that, for example, you could look at oxygen isotopes, and that would be a very straightforward offline calculation, or you could even fully embed it in the model. Have you done something like that so that we can actually test the sort of things that you're inferring for the freshwater fluxes and so on?
I'm not entirely sure if I understand the question. So you want to, so what do you want to test?
So
exactly?
you basically have your freshwater fluxes into the basin and how they actually affect the different boxes, etc. But especially where they affect the surface boxes, your positive and negative freshwater budgets, etc. Those things you could test with the oxygen isotopes in planktonics, and you could, I think, make a very simple routine to get a first order test of what you're inferring. Have you considered this?
Yeah, we have definitely considered an oxygen isotope model. It's also something that we're looking into for future research. But to do that, we first needed the water model. Mm-hmm. And this is an extra layer on top, and well, we didn't have time to do that. Okay, so yeah, okay, fair enough. How are we going?
Still have time for questions.
Yeah.
Yeah.
Okay, I have some minor points. Throughout the thesis, you basically talk a lot about the Nile. Now, the Nile comes into a very specific location into the basin. There's a lot of information around that there was general freshwater release along the entire African margin, and some of it, not negligible against what the Nile would have been pumping in. Have you considered how that would, that spatial distribution would affect your outputs? Yes, I have. Yeah. So everything that runs off from Africa ends up in what would be in the model the open box. Yeah. Right. Okay. So whether we call that the Nile or runoff from Africa is well, in the model it's all the same. Yeah. And we have tested a very broad range of outflow. Yeah. So in that sense, we did test for it. Okay, so you're basically using Nile as a placeholder for African runoff, yeah. Exactly, yes. Yeah, because there is a possibly an important distinction to be made when you do the nutrient modeling. The nutrient flux from these different rivers are very likely to be very different. Yeah. Yeah. Okay. Get a fire on? Okay, well, this is going great. Yeah. So in section 321, you state that the use of constant volume for the boxes implies that we, and essentially you then explain what that means. You have constant volumes, etc., between surface and intermediate, and the deep cell. But there's a lot of evidence that the volumetric capacity of these boxes has changed. That's basically the intermediate water coming up to about 50% shallower than it is now. How would that affect your results, do you think? So the volume of the boxes is not super critical, but then of course the question is like, how does that change the transient response of the model? Mm-hmm. Because if it's just static, then it's not a big deal. So one of the things that I would mainly expect is that so there are these transitions in the model, right, during the sepropel phase, or there can be at least, when fluxes reverse. And then the model or fluxes stop. Then the model relaxes towards a new equilibrium. And the time that it takes to relax towards a new equilibrium depends on the magnitude of the fluxes and the volume of the boxes involved. Yeah. So if the volume of the boxes changes, then the equilibrium time changes, basically. Yeah. Okay. Good. And you have considered how this would potentially change conclusions, or? I find it very hard to say because I haven't done these tests, and it would be a different model. So I would so it depends on. So how do you expect, for example, that
the intermediate water volume changes throughout the precession cycle.
Well, that's a big question, the intermediate water volume, but the surface box is likely much shallower. And as a result, you actually get the action of your freshwater input, but also evaporation on a smaller volume of water.
Right, but the equilibrium time of the surface box is very short in relation to the rest of the model.
Mm-hmm.
So making that, like, even if it halves, then then the equilibrium time is maybe, let's say, I'm not entirely sure what it is, but probably something in the order of like 50 years.
Mm-hmm.
So if it becomes 25 years instead of 50 years, then that doesn't really affect the rest all that much, I think.
Okay, thank you very much.
Thank you, Professor Rowling. The discussion will be continued by Professor Schiero from the University of Salamanca.
Good morning. Dear candidate, one of the main questions you try to answer with your models is how from a gradual change in the freshwater budget you get a fast response in the trigger the subrepel formation. But have you considered the possibility that this the forcing mechanism can be just a sudden, could be related to sudden change in for example, in temperature or not the freshwater budget, because you analyze in one of your models, you analyze the impact of temperature on the deep water formation in the Mediterranean. But you increase the temperature from a gradual change also from, I think, from 10 to 13. I don't know exactly why did you choose these temperatures. In the open box, you choose from 10 to 13, and in the marginal basin, you choose a change in temperature from 12 to 15. How did you choose these temperatures? It was based on winter temperatures or?
Hooggeleerde opponent, thank you for your question. It's, so we, to make the model work, because we take time steps of 1 year, we need to assume perpetual winter conditions, because the deep water formation happens in winter. And if you assume summer conditions, then there would be no deep water formation, and then the model doesn't work. And well, we know that there's a temperature gradient, because you're at the margins, you're at a higher latitude.
Mm-hmm.
So it's colder there. And then we did a sensitivity analysis to see how that affects the circulation. And the values that we eventually chose were the ones that seemed realistic to us, also based on literature.
Mm-hmm. And well, my question mainly is related to because we found maybe 2 years ago, we found that some of the subrepels apparently start at the time of abrupt warming in Greenland, especially S3, S4, and S5. We were studying the Mediterranean outflow in west of Gibraltar, and apparently the onset of the subrepel is related to abrupt warming in Greenland. That means that the temperature in this case doesn't change gradually, and it was just a very fast change in temperature. Mm-hmm. Can you comment on the possibility that this abrupt change in temperature, air temperature, can impact your model? I don't know, instead of a gradual increase in temperature, just an abrupt increase in temperature, and if this can make an impact on the formation of the subrepels, especially these 3 subrepels.
That's a good question. So it depends on how large the temperature increases, and also on the state of the Mediterranean at that time when the temperature increases. Because if you're already very close to a stratified state and you suddenly increase the temperature, then that might trigger a transition to a new circulation state. But if you have a very strong circulation, then the temperature change is unlikely to do much. And well, it will still slow down the circulation a little bit maybe, but nothing significant. So the question is basically how close are you to one of those transitions, and is the temperature increase enough to trigger the transition? Mm-hmm. And if it is, then yes, it could, yeah.
Because normally, especially in the late Pleistocene, well, today normally the convection only occurs those winters where the temperature is really cool, because the temperature of the deep water is more or less 12, 13 in the Western Mediterranean. But if you suddenly increase the air temperature, then you get warmer temperatures at the surface in the beginning, but it's still the temperature in the deep waters is cold. I mean, in this transition, there should be a kind of stop in the water formation. I assume that this may be an impact on the Mediterranean circulation.
Yeah, I think it could definitely impact the circulation. Yeah, I agree.
And what about also the interruptions in the subpropels? I mean, you talked a little bit about this, but especially in subpropel 1, there's a short interruption in the middle, and it's also related to cooling in the northern hemisphere. Of course, it may be also related to freshwater budget, but what do you think about this? Maybe also because if you decrease the temperature, the air temperature at that time, then you get higher contrast in the density between the surface and the deep, and then you increase the water formation.
So,
do you think the temperature has an impact on this, or maybe it's just the fresh water, maybe the fresh water coming from the Nile? Or
yeah, so the fresh water and the temperature can have a very similar effect, so it can be hard to differentiate between the two. And one of the things that we have been doing since the thesis is using a titanium aluminium record from the Eastern Mediterranean close to the Nile as an input for the model. So then we scale the titanium aluminium and we smooth it, and we use that as the river outflow for both the Nile, or runoff from Africa, and the rivers from Europe. So all the river outflow is just scaled to the titanium aluminium record. And if we do that, then for most of the subpropels that are not deposited during a glacial, the model gives a very accurate prediction, and it also shows most of the interruptions. So that would suggest that, and there we didn't vary the temperature. But as I said, like the temperature and salinity have a similar impact. Like they can, if they're both working in the same direction, then they harmonize. They both do the same thing. So it could also be that the river outflow variability is a bit smaller and the temperature variability a bit larger. That's also possible, but yeah, it's possible. And
what about the meltwater? Because you didn't run a model for the meltwater inputs in the Mediterranean, but as you said in your thesis, there's almost no evidence of meltwater during subpropels, but there is a lot of strong evidence for meltwater input into the Mediterranean during some deglaciation, in particular because of the meltwater that is coming from the ice sheets. But apparently there is no subpropel associated to this meltwater. Maybe I don't know, maybe subpropel 6. But what do you think about the impact of meltwater? I know you didn't run the model for this, but what do you think? Why there's no subpropel formation coinciding with these events of meltwater in the Mediterranean? Maybe salinity, or I don't know. Maybe temperatures too, or.
That's a good question. Well, first of all, like I haven't run the models for that, so I don't know. But yeah, then you would really have to look into how the variability also in the Atlantic affects the Mediterranean, and yeah, there might also be more runoff. But I think one of the key points in the thesis is also that during when it's not in a subpropel state, so like the current circulation, it's really hard to go to that subpropel state. You need a lot of river outflow over a long period of time. And maybe if there's a meltwater pulse during like not the ideal moment, let's say, then yeah, it becomes slightly less saline and maybe the circulation slows down a bit, but it's not enough to go to a subpropel state.
And
short question, concise answer, please.
Yeah, I'm curious about because in your model about the Black Sea, there is when you start the two-way exchange between the Black Sea and the Marmara Sea, you get a strong convection event in the beginning, I mean, the first 2,000 kiloyears. Why this? Because, I mean, do you see the salinity of the Black Sea increases because of the salt that is coming from the Mediterranean? And apparently there's some short interval in which the salinity of the upper and lower boxes is the same. I don't know exactly why.
Yeah, that's an interesting question. So part of the water that flows into the Black Sea from the Sea of Marmara and the Mediterranean gets entrained into in the intermediate and surface water. And the intermediate and surface box is much smaller than the deep water box. So even though a smaller fraction goes to the surface and intermediate water, the salinity there increases faster than in the deep water. So then the density increases at the surface, and then you get convection, until at some point the salinity in the deep water has increased so much that the river outflow into the Black Sea stops the convection again.
Thank you.
Thank you, Professor Schiero. The discussion will be continued by Professor Vlecker from the University of Bristol, and she will be joining us online. You're muted, sorry.
Dear candidates, can you hear me? Can I just start by saying that I really enjoyed reading your pieces. I was particularly impressed by the integration. Sorry, I'm getting a lot of feedback. Are you hearing feedback too? Okay, I'll just ignore it mine. So I was particularly impressed by the integration of the core-based chapter 2, with the modelling chapters that followed. And in this regard, what I'd like to discuss with you are some of the things that come out of your synthesis chapter in particular, that integration chapter, which I found quite provocative. So I'd like to start by asking you a little bit around the observation that you made about the transition, the impact of the transition to a positive freshwater budget. The observation that you make is that you can transition to a freshwater system without immediately resulting in a reversal in the circulation system and the exchange configuration. How long do you think, given the model simulations that you run, how long is it possible to maintain that scenario? So change in budget with no change in the exchange configuration.
Hooggeleerde opponent, it's a very good question. It depends on how positive the freshwater budget becomes, because like if it's zero, then it never transitions, and if it's really high, then it transitions almost immediately. And it also depends on the state of the circulation when the freshwater budget becomes positive, and like what the characteristics of the deep water and intermediate water are. But typically, I would say in the order of a few thousand years. Or like, well, for example, in S5, it's like right at the edge of almost transitioning. So that's like 7,000 years off the top of my head, something like that.
So I mean, that has really quite important implications for Mediterranean overflow, for example, into the Atlantic. And would you like to comment on what those implications might be?
Sorry, I don't completely understand the question.
So if we have a situation where, in essence, you have, as a consequence of having a positive freshwater budget, not a massively positive one, but enough to cause the exchange not to transition but to cease, that presumably impacts Mediterranean overflow. In other words, we're looking at intervals where there is none. Is that what you are saying?
When the delay is also because when the freshwater budget at the surface becomes positive, then the convection with the intermediate water stops, and that means that the intermediate water is now more or less isolated, so that it only increases density, or the density only decreases very slowly because it's only basically through mixing and exchange with the Atlantic. And I'm not entirely sure like what you're going for.
So are you? No, I think you're absolutely going where I want you to go, and I appreciate that I'm poking you in directions that you perhaps didn't necessarily consider. That's fine. That's what I'm after. So What is it, as I understand it, that you are saying that the impact on overflow as a consequence of that relatively slow change in density of the intermediate box would mean that any cessation of overflow would post-date the change in the budget, the hydrologic budget?
Right, yes. Yeah.
And that what we would actually see is a decline in overflow initially rather than a cessation. Is that correct?
So the actual transition can be very fast. Like if you look at the graph on page 102, for example, figure 5.2, then you can see like when the freshwater budget becomes positive, then it's a relatively gradual change. Yeah. Well, it also depends on what you're looking at. So, for example, the temperatures are they transition pretty quickly, especially for the margins, because that's where the freshwater budget becomes positive. But the fluxes themselves are much slower.
Yeah. Okay. And then again, slightly to pick up on something that Professor Rowling talked about earlier, which is the kind of the potential test of this sort of scenario. You mentioned again in your synthesis chapter the potential application of this model to smaller basins like Sorbas, for example. And there was a paper published in 17, I think, by Modestu et al., which used a similar model to the one that you've developed yours from, which looked at the strontium isotope implications. And that too shows some quite interesting data that is compatible with this concept that actually horizontal exchange between a marginal basin and the main basin can, at least cease to such an extent that actually the isotopic behavior of strontium isotopes indicates there is, a lack of connection. Is that a paper you're aware of?
I think so, yeah. The name Modesto definitely rings a bell, but it's been a few years, so I'm not entirely sure what the...
Well, I think it would be a really interesting thing to do is to actually have a look at the difference between the model that they used, again, to study this transient behavior, and your own, and to see how actually your work then improves our understanding of this. And then finally on this topic, and I suspect I'm going to run out of time on this one, have you considered the implications of your model simulations for a gateway system which is much more restricted? So let's move you now from a Sackapel scenario into the Messinian salinity crisis. How does your model, you can postulate, because I'm sure you haven't run all these, but think through the implications for a much more saline system, or potentially a much more brackish water system, which is of course what we get at the end of the MSc. How do you think it would play out?
So if you purely look at the restriction at the strait, then unless you make it about 1,000 times more restrictive, you basically get the same outcome, except that the exchange slows down. Because like when the density difference increases because it's more restricted, you get the exchange increases because it depends on the density difference. Yeah. So for the Mediterranean Sea itself, the restriction is not all that important. Except when you go like if it's really restricted, then at some point it starts to behave completely differently. So but it's a very sharp transition, at least in the model that I tested that with.
But you do have a situation under those circumstances where you have much larger salinity contrasts.
Potentially, yes. But although from the runs I did, so unless you go to that really different situation where it's super restricted, I don't think the salinity contrasts were that big. Okay,
all right. And in terms of the positive freshwater budget, again, are there any implications, particularly for that last phase of the MSc, where we're dealing with at least episodes of brackish water conditions? Are there things we can learn from your modelling that might be applicable to that?
Well, the general idea still applies. So, yes, you can definitely learn things from that. But the situation might be a bit different because, I'm not super familiar with the MSc, but there might also be residual brines, right, in the deep water.
Yeah.
And so those might affect the circulation as well, and that's something that's not captured in the model currently. So, so it's a slightly different situation.
Thank you. I suspect it's my turn to shut up. Is that right?
Yes, I'm sorry, we have to continue. Thank you very much, Professor Vlekker. The discussion will be continued by Professor Regaard from this university.
Dear candidate, let me start with complimenting you on this nice thesis which is laying in front of us, especially with these beautiful pictures taken from our national research vessel. It's a good overview of how you started in this subject. I also have some questions, and then I would like to especially to go to chapter 4, in which you use you couple your model for overturning to a biochemical model, and you use basically the biogeochemical model, which was developed by Caroline Slomp and Philip van Capelle.
Yeah, more or less.
And you use the phosphorus as basically the nutrient to use. Could you explain to me the overall rationale for using phosphorus instead of nitrogen?
Hooggeleerde opponent. So this was the main limiting nutrient. At least that's what I understood from.
Yeah, but why is phosphorus the main limiting nutrient? Can you explain that to me?
Well, that's a good question, and this is mostly for the nutrient model. I'm also relying on the expertise of my co-authors. So I don't have a direct answer right now.
I can give you the answer. I mean, it is basically because you have, if there is still phosphorus and there is no nitrogen, then on geological timescales, the nitrogen will be produced by
I don't know.
the nitrogen-fixing algae, the diazotrophs and so on. So you always have, on geological timescales, there will always be enough nitrogen for the productivity. So then you can take phosphorus. I think that was a good assumption in your model. So, but it also comes with some consequences. Because there are, so if these diazotrophs, if they are fixing extra nitrogen, where do you think they do this?
I would expect mostly at the surface.
Yeah, definitely, because they have to you have to photosynthesize.
And probably also mostly in the margins, because that's where the nutrients mostly are.
Could be, yeah, for instance. Yeah. And have you heard about recently in the news, maybe, that there are some places also in the Atlantic Ocean where there is a very high productivity?
A bit, yeah.
Those are the blobs of fresh water which are basically going out of the Amazon River, which is fresh water, and then can you already see what is living in those freshwater blobs?
The nitrogen-fixing bacteria?
I think so. So what would be the consequence for your model if you have a freshwater lens? Would it affect the thingy, or is this your outcome in chapter 4 or not? Can you speculate a bit on that?
That's a good question. So for the margins have very little effect on the main basin. They're mostly decoupled in the model because you always have a positive freshwater budget, and it's just one box, so that doesn't really do it much. In the main basin, the fresh water gets distributed pretty quickly by the currents there, so we assume that it's uniform. So then the question is really like, where does the productivity take place, right?
Yeah, or where you have the extra nitrogen fixed, so that you have with the same amount of phosphorus can still make enough more organic matter. I mean, basically that's the main question, I guess.
Yeah, that's a good question. I don't know how the model would respond to that, to be honest.
Okay. And is this now limiting your model also to the use? If you can you now export the model basically which you developed for the Black Sea? Would that limit it for the use into the Mediterranean?
It would definitely need some tweaking. I don't know. I'm not sure if it would, if this thing that we're discussing now, how that would impact the circulation in the Mediterranean. I find it hard to say. But otherwise, I think you could definitely apply this model, slightly adapted form, to the Mediterranean.
Okay, because in the Mediterranean, I know that if you go to subpropels, you find a lot of those, of course, this phosphoglycolipids, which basically are associated with the diazotrophs which do the fixing of the nitrogen. So I think I would say, well, for the Black Sea, I believe your story, but for the Mediterranean, I would still wait a little bit.
But then you would have to add maybe the nitrogen as well.
Okay.
Yeah.
Let's jump to another subject.
Okay.
I was wondering, you are looking at the rapid response of the system, and you nicely combined here. I think this is also on page 109. You can see there's different high frequency changes, and then you see that you're able also to find different high frequency changes with your model, right? Is that correct?
More or less, yes.
I was wondering, because I think it's a nice way to explain. I think that was also already mentioned by Professor Sharrow, of course, that there's a non-linear forcing, and then you get this this tipping point kind of behavior. Can you also use this to investigate kind of variability before the onset of the subpropel?
So in the model, well, let's look at the figure on page 109. So before the subpropel, there's basically just a linear response. So in the model, there's nothing really going on until the moment where the deep water formation stops.
But we do know from the papers from Brechtje Bolt and Rick Hennekamp that there is some kind of already this kind of behavior before the onset of the subpropel. There are some kind of precursor kind of behavior in which you can statistically model this kind of thingies. Would you know a way of approaching that with your models?
Well, I think that mostly implies that the model as it is now doesn't capture that behavior. So then you would have to look into what is actually causing this precursor behavior, and well, I don't know.
Okay.
I don't know if you know. Maybe you know, and then we can say more.
I also don't know. I was just curious if you could tweak your model in such a way that you could get this kind of behavior, because of course it's very intriguing.
Yeah,
and that you have already before the onset of the subpropel, you see things happening, and I'm wondering what is it?
Yeah, so am I.
I think my time is over, eh?
About, yes.
Okay.
Thank you very much, Professor Reichert. The discussion will be continued by Professor Laurens.
Dear candidate, I also have read your thesis with great interest. I would like to continue the discussion on your Outlook chapter, chapter 6, particular figure 6.1, on page 116. If I look at the y-axis, you have plotted here your total freshwater budget in meters per year. And if I'm correct, this is E minus P minus R, is that correct?
Yeah, I think so, yeah.
So when you have actually higher values in your total freshwater budget, you actually have lower freshwater in the basin, isn't it?
We have higher freshwater budgets. So this is the... let me think. So you're saying that if the freshwater budget is higher, more positive, then the salinity becomes lower.
Yeah, so just for an example, if you look at, for instance, 125 kilo years before present, that's the S5 subpropel, and then you have a very low freshwater budget in the basin, but to my opinion, that should correlate with higher runoff in the basin.
Yeah.
I was just wondering if the term total freshwater budget is a good way to express this.
I think this should be net evaporation. Then,
yeah.
That's it, probably. It's not a mistake. Yeah.
Will also be my guess. So I was intrigued by this curve you made from the core data, and I think I already understood that that was based on titanium aluminum. Is that correct? Because it was not mentioned.
So, yeah. And it's moved a bit.
So if I look at this blue curve comparison to your sine curve and the 21 kilo year cycle you plotted, then in the blue curve, I see actually a combination of two sine waves. Can you see that too?
Well, more than two sine waves, but yes. Like it's a harmonic spectrum. Or not necessarily harmonic, but it's a spectrum.
Especially in the let's say the long periods.
Yeah.
Yeah. What is the second one?
So we smooth this out, right? So there's I think it mentioned it somewhere which filter I used, but anyway, so the actual data is a lot more irregular.
Mm-hmm.
And it has harmonic content, so so you can probably see like a second order harmonic in there.
Is it? If I just for an example, if I look, let's say your total freshwater budget around 82 kilo years is very small, and then the one at 105 is a little bit more, and then at 125 it's very low again, and then 145, it's
So
higher
there is
again.
so in the core signal there is also obliquity, of course, and
Right.
eccentricity. So there's that. That's probably the more like the longer term variability.
Yeah,
But you can also see, for example, at about 85 kiloyears and about 105 kiloyears, and also at 122, like you see in the troughs you get like a small peak, and those are the second order harmonics.
Yeah, so okay, I see that. So more the high frequency variability. So I agree with you that is probably obliquity additional forcing, and is what you can see nicely in the record. So how can you explain obliquity forcing on your runoff in the Mediterranean? Do you have any idea?
Well, apparently it affects the river outflow, it seems, and how that exactly works, I'm not entirely sure.
Okay.
But yeah, it's a complex system. And it's sort of so we modeled what happens in the Mediterranean. That's what I mainly looked at, and then the rest is the boundary conditions basically.
Okay. Yeah, we have done some model simulations on this in the past, showing that probably you also have an obliquity component in the monsoon system itself, so in the climate forcing itself. Let me see. Okay, so one additional comment: if you use titanium aluminum from this specific core, we know from other cores that the pattern in this particular area you have very strong amplitude fluctuations titanium aluminum, because that also depends on, let's say, the dust tracks which apparently pass this location. But if you go more to the central part of the Mediterranean, these amplitude variations are much smaller. So can you actually just use this specific location to say something about your total freshwater budget in the Eastern Mediterranean? Or is that a little bit too optimistic?
So the idea is that a large part of the freshwater budget is the Nile variability. Also in the model, like the way we use now, the main variability is from the Nile and the runoff from Africa in general. I think for the Nile, this is a very sensible record because you're close to to where it flows into the Mediterranean. So it's a sensible location. And for the rivers from Europe, there are not that many. They're not that great, quantitative reconstructions. So there we basically had to make an assumption like how they vary over time. And then we do know that it's more or less in phase with the Nile outflow.
Right.
But we don't know like what the exact amplitude is and the means and the minima and maxima. So then we use that signal. And if we do that and use this whole titanium aluminium record, then we get a good result for so this is not in the thesis, but then all the sapropels fall in the right place except for during the glacial.
Right. I agree, but if you look, let's say, if you use titanium aluminum, so aluminum I can imagine that you can correlate that to now outflow, but the titanium comes mostly from Northern Africa, so from your desert. So that relates much more to the evaporation, let's say, in that area, the dryness of that area. It doesn't tell you anything about, let's say, the total runoff. So I'm just wondering if you can use this as input for your results. If I have time, I would like to go to your figure on 102 and ask a little bit about the time lags you simulated for the midpoints of sapropel. So you have a precessional forcing, and then what you can see in this figure is that, let's say, you have your optimum in runoff or in your freshwater budget around 10 kiloyears, half your wavelength. And then if you look at the sapropel midpoint, which is illustrated on top, that would actually suggest that the midpoint would, let's say, precede your forcing. With, let's say, 500 years or something like that. And I think you also discussed that previously in another chapter. What we see actually is that the sapropel midpoint actually lag insulation forcing by 3 kiloyears, in particular for this time interval. So how can you explain, let's say, this offset between what we actually observe in the record and what you simulated here?
That's a good question. So you have to understand there's a difference between the forcing that we use in this chapter and the actual, what actually happened in the past. So for this chapter we use a sine wave forcing because that's relatively straightforward, and then you can see what happens, and the behavior is already very complex, and now we can still understand why the things are happening that are happening. And if you use a And the actual record has a different face and different shape, so then you get different results.
Thank you.
The committee will now withdraw for further deliberation. The session is adjourned. I hereby reopen the session. Mr. Doctoral Candidate, this committee, installed by the Board of the Conferral of Doctoral Degrees, has considered your dissertation and has heard your defense. The committee has decided to confer on you the title of doctor. I now kindly ask the supervisor, Professor Krijsman, to invest you with the honors in the traditional fashion.
Uit kracht van de bevoegdheid ons bij de wet toegekend en volgens het besluit van de promotiecommissie hier tegenwoordig verklaar ik bij deze u, Jan-Pieter Dirksen, te bevorderen tot dokter met alle daaraan door de wet en de geboonte verbonden rechten en plichten jegens samenleving en wetenschap. Belooft u dat u altijd volgens de beginselen van wetenschappelijke integriteit te werk zult gaan, eerlijk en zorgvuldig, kritisch en transparant en onafhankelijk en onpartijdig? Dan overhandig ik u nu het diploma door rector en promotor en co-promotor ondertekend en van het grootzegel der universiteit voorzien. Hartelijk gefeliciteerd. Nu nog een speciale foto.
Mr. Pieter, Dr. Dirksen. The defense has been in English, and I will switch to Dutch in just a minute. And for that, my apologies to Rachel and to Paco. But before doing this, before going towards the other language, I would just like to point out how grateful I am with today's composition of the committee. It was only when we had the list together that I realized that Wout and I had managed to get together a group of colleagues that really have been, through their work, their publications, and in discussions, sometimes going back many years, have been inspiring and steering our work. Beste Pieter, in 2017 kreeg ik, dankzij een van de laatste hoeken uit de zak met ISIS-geld, de gelegenheid om een kandidaat te gaan zoeken voor een nieuw project. Een project gericht op het numeriek modelleren van sapropelen. En ik wist uit ervaring dat het best lastig was om voor dit soort werk toch goede kandidaten te vinden. Je zoekt iemand die een mooie combinatie is, dus de ideale kandidaat die vormt een combinatie tussen vertrouwdheid met de data, met observaties, en is handig met de computer, heeft aanleg voor het numeriek modelleren. In jou heb ik die ideale kandidaat gevonden. Ik werd getipt door Gert-Jan Rijgaard en Riek Hennekam. Op dat moment was je onder hun begeleiding op het NIOS bezig met het afronden van de stage. En die stage die was gericht op het ontwikkelen van een nieuwe analysetechniek, gericht op een kern gezet in de Oostelijk-Middellandse Zee. Dus je was vertrouwd met de observaties. Sterker nog, het is al te sprake gekomen, je was aanwezig op het schip waarbij de betreffende kern werd genomen. En bovendien had je op het NIOS en ook al eerder op de Universiteit Utrecht laten zien dat je zeker aanleg had voor het modelleren. Nou, ik heb in de afgelopen jaren regelmatig gerealiseerd hoe goed het was dat jij op dit project bezig was. Je hebt verschillende keren laten zien in je keuzes van, soms ging het gewoon om een aspect van het model of om het formuleren van een vervolgvraag. Ik had heel sterk de indruk dat dat werd ingegeven door je vertrouwdheid met het echte probleem, met de echte data. Wat ik niet op voorhand kon zien en wat al snel bleek, is dat in het onderwerp harmonische golven voor jou een heleboel dingen samenkomen. Het is niet alleen werk en wetenschap, het is ook persoonlijke fascinatie en zelfs hobby's. Meer dan eens heb je er mij proberen van te overtuigen dat de thermohaline circulatie van de Middellandse Zee echt hetzelfde werkt als een elektrisch circuit. Ik geloof dat degene die daarvoor verantwoordelijk is vandaag op de eerste rij zit. En elektronica en golven komen ook terug in jouw grote hobby, het maken van muziek. En eigenlijk wacht ik nog steeds op het moment dat we de sapropel, de proxy record niet alleen kunnen zien in complexe grafieken, maar dat we er ook naar kunnen luisteren. Die stap die ontbreekt nog wat mij betreft. Goed, het werk wat ik al noemde op het NIOS, dat is het eerste inhoudelijke hoofdstuk in je proefstuk geworden. Daarna ben je aan de slag gegaan met het numeriek model. En daarbij heb je een eenvoudige basisgedachte heb je opgepakt. Het idee was om juist met een relatief simpel model te gaan werken, zodat we nou eens een keer in staat zouden zijn om het proces helemaal door de tijd te volgen. Nou, je hebt laten zien dat dat kan, dat het werkt, en je hebt ook laten zien dat het belangrijk nieuw inzicht oplevert. Toen je die stap af had, toen je dat eerste modelstudie rond had, Toen waren er heel veel mogelijkheden. Ik kan me goed herinneren een meeting waarin we gewoon een lijstje aan opties opstelden. Je hebt ervoor gekozen om het model te gaan verfijnen, door een extra waterniveau toe te voegen, zodat je in staat was om iets te zeggen over de relatie tussen de relatief lange tijdschaal, precessie in ons geval, en juist variabiliteit op korte tijdschaal. Een interessant aspect. Bovendien heb je er zelf voor gekozen om iets wat een hele simpele parametrisatie was in je eerste model, en dan heb ik het over de zuurstofconcentratie, om dat verder te willen uitwerken door je watermodel te koppelen met een nutriëntenmodel. Dat is een belangrijke conceptuele stap geweest. Je hebt die gezet samen met Caroline Slomp, die er vandaag helaas niet bij kan zijn omdat ze op zee is op dit moment. En ik vind het heel erg mooi dat je zover bent gekomen, dat je die stap ook daadwerkelijk hebt kunnen zetten. Pieter, toen je begon als promovendus, dan heb je op een gegeven moment je kamergenoten uitgelegd dat je van plan was om iedere dag vanuit Hilversum op en neer te gaan fietsen naar de Uithof. En toen heeft Dirk Simon, een van jouw voorgangers, die heeft uitgerekend dat als je dat 4 jaar zou volhouden, dat je dan een afstand zou afleggen min of meer gelijk aan de omtrek van de aarde. Nou helaas, je was zo'n beetje de tweede keer de evenaar gepasseerd en toen kwam er voor jou in het dagelijkse ritme een belangrijke onderbreking. Niet alleen voor jou, voor de hele wereld. En juist een heel druk jaar zat je opeens thuis. Een druk jaar, ik herinner me, je had een fieldtrip, een geologische excursie op Sicilië. Je hebt ICP bezocht in Australië, daar heb je collega's van Elko Roling ontmoet. En samen met je parenimf Ronja Eepner heb je nog een paar studenten ook begeleid in een speciaal studentenproject. En dat was opeens voorbij en toen zat je thuis. Nou, zeker als je weet dat er voor jou nog een andere kwestie speelt op gezondheidsvlak, denk ik dat het terecht is dat ik vandaag even bij stilsta. Hoe knap het is dat je hebt volgehouden. Je hebt doorgezet in die moeilijke situatie en het is je gelukt om een heel mooi proefschrift af te leveren. Goed, uit alles wat ik heb gezegd blijkt dat je werk veelzijdig is geweest. Het is een eenvoudig model, het is al een paar keer te sprake gekomen. Het blijkt als je dat een klein beetje gaat uitbreiden dat het dan gauw juist heel complex wordt. Vergt zorgvuldig denkwerk en vergt ook heel secuur programmeren. Je hebt ervoor gekozen dat het programmeren het onderwerp te maken waarop je verder wil in de toekomst. En inmiddels werk je als software engineer. Ik zal eerlijk zeggen dat het me een beetje verontrustte dat je me vertelde dat na een paar maanden training op de nieuwe baan, dat je al behoorlijk kritisch keek naar je eigen modellen. Maar ondertussen denk ik wel dat je daar op zijn plek zit en ik wens je veel succes. Pieter, het was een voorrecht om met je te mogen samenwerken. Je hebt een eenvoudig idee naar een hoger plan getild. Je hebt een proefschrift afgeleverd wat vol zit met aanknopingspunten voor interessant vervolgwerk. Ik wens je in je werk en privé veel succes en veel geluk. En ik eindig met je te feliciteren. En die felicitaties gaan uiteraard ook uit naar je familie en vrienden. Gefeliciteerd.
Very learned sir, on behalf of the Board of Conferral of Doctoral Degrees, I congratulate you on the honors which have been bestowed on you. I hereby conclude this session. I would like to invite Professor Vlekker, Rachel, to give you some compliments.
Well, thank you. It's been really great to be part of this situation, this defence. I've really enjoyed it. I've really enjoyed reading your thesis. I look forward to seeing more of it published in due course. Many congratulations.
Thank you, Professor Vlekker. And the ceremony is now closed and we are going elsewhere. And I give the floor to our Bino.